Okay, welcome everybody. It's my pleasure to invite and introduce Koven Yu. He's currently a PhD candidate, graduating candidate from Stanford, advised by Jia-Jun Wu. His research focuses on physics-grounded world models. He's also the recipient of the SIGGRAPH Asia Best Paper Award, the Stanford School of Engineering Fellowship, the Qualcomm Fellowship, as well as the Meshi Fellowship. Take it away. Welcome.
Yeah, thank you, Ranjay, for the kind introduction, and thank you everyone for coming. So today I'm going to talk a bit about my work on physics-grounded world models. And well, world model is one of the hottest topics in AI nowadays. With world models, you're able to create 3D worlds, you're able to simulate physical interactions, and build interactive virtual environments. Well, and we have really seen this explosion of research work in both industrial labs and academia labs. And they did show very impressive visual results. But back in 2023, when I started working on Wonder Journey, which was the first work on open world 3D scene generation, none of this work really existed. So there were no startups, no other papers, and no wonder or world in every single paper's title. So how did I get there? Let me take you back to where all this started for me. So this traces back to my childhood. I was born in a small village back in China, and as a kid, I had this huge curiosity about the world. But I didn't really get a chance to get out of the small village. So instead, I spent a lot of time reading storybooks and tried to immerse myself in those virtual worlds. And among all of them, Alice in Wonderland is one of my favorites because the world it described was so fascinating. But here's one thing that always frustrated me. It is when Alice falls down the rabbit hole, the book tells you that she falls down. But I wanted to look around. I wanted to see all the walls rushing past me. And when Alice sits down at the tea party, I wanted to knock off the teapot off the table and see how it shatters on the ground. So I really wanted to be there rather than just reading about it. And this frustration actually stuck with me because that pointed to something fundamental. We learn about the world not by only reading descriptions, but also by looking around, by touching things, and by seeing how things respond when we act. That's how we build our intuition about the world. And that's what motivates my research, building virtual physical worlds that you can freely explore and interact with, which I call world models. But actually, nowadays, people use the term world models pretty differently. So it is admittedly an overloaded term. For example, in Ian LeCun's formulation, a world model predicts the future state in some latent space. And more recently, video-based world models such as Genie defines it as predicting future video frames. Well, these are both very exciting directions, but neither of this was really after what I was chasing. That is, freely exploring and interacting with a world. Predicting latent states or predicting future video frames doesn't give you the 3D structure that you can navigate or give you the physical actions that you can take. So here's my definition of a world models. That is, it should recreate the 3D physical world and simulate how it responds to our actions. But I also want you to know that now it is still very early days for world models, and the definition will likely depend on specific domains. Anyway, what does my definition of world models actually look like? Now, here's a 3D world that is generated by my work. You can freely move around and change your viewpoints in real time, and even you could create new contents in those when you explore to new unseen areas. And once you have this world generated, you can interact with it. You can apply physical actions, whether it is a robot interacting with some objects or abstract 3D forces or force fields like wind or gravity. And then you can observe how the world responds to your actions. So how do we achieve this goal? Well, in some sense, this goal is the big dream of computer graphics and the robotics community. So in the past several decades, people have been building physical models and softwares like Blender, like Isoc-Gene, Omniverse, and so forth. Now, this approach gives you the full control over physics and over the actions, but it requires significant amount of manual effort to author each scene. And also, even if we have this significant amount of effort, that still leaves a significant gap of visual appearances in terms of the simulation environments and in real worlds. because physical models inevitably need to make approximations and simplifications to make the computational model tractable. For example, here I'm showing this multi-material interaction example from Isaac Gene. And you can see that multi-material interaction is still pretty hard to faithfully simulate. And recently, end-to-end generative models, like video models such as Sora from OpenAI, or Veo from Google, or controllable video models such as Genie from Google, has shown creating realistic and diverse contents. But these models also suffer from fundamental limitations. The first fundamental issue is that there's basically no guarantee of physical consistency. Now, in this example, I ask Sora 2 to generate the scene where you have multiple dogs. But you can see that the multiple dog can merge into one dog, and one dog can split into multiple ones. And then a dog can disappear after occlusion has happened. So you might argue that, oh, can we scale up video models and video data to address this? Well, you could do that to further improve the fidelity, but there's simply no guarantee for such end-to-end neural networks. And this guarantee is actually important for many of the downstream applications. And even if you could scale up video models and to improve all the quality, you still face another fundamental limitation. That is, all these end-to-end video models cannot accept physical actions as input to simulate the physical interaction with the environments. So in this example, I asked Veo 3 to push this cup by 10 centimeters to the right. Apparently, it is not pushing it. It is not to the right, and not by 10 centimeters. And fundamentally, this is because we generally do not have physical action and video pairwise data to train it. And in fact, how to represent physical actions and to collect such data is itself an open problem. And these two issues actually share the same root problem. That is, when you entangle your world states, your dynamics, physics, and the rendering into a single black box neural network, then you lose the structural interface for you to impose physical constraints or to interface with physical actions. So end-to-end generative model also suffer from these two fundamental issues, that is the lack of guaranteed consistency and the interactability with physical actions. So all this motivates my research, that is physics-grounded world models. And the key idea here is to integrate physical modeling with generative learning so that we can get the best of both worlds. And the key insight here is not just combining the two approaches, but to recognize that they actually fail in different ways. So physical models fail when physical states are incomplete. For example, when you have missing geometry or unknown material or lighting conditions. So filling in such all this missing information takes the heavy manual efforts. And generative models, on the other hand, have actually learned rich knowledge about the world from internet scale data. And this will scale up with the time passed on. But such knowledge is trapped in pixel space. So you cannot simulate it, you cannot act on it, and you cannot guarantee consistent with it. So the key insight behind my research is that we can distill the physical knowledge learned by these generative models and then ground it in explicit physical representation so that it can become actionable, simulatable, and consistent. Now let me walk you through how this works at the high level. At the core here are explicit physical representations that capture the physical property and the appearance properties of the world. And from these, we can render pixel-level visual observations. But as we discussed, pure physical models leaves this significant gap between the simulation environment and the real environment. So this is where the generative models come in. They refine and enrich the rendered output with the rich visual knowledge that it learns from internet scale data, and then ground it back to the physical representation. And again, when the physical action is applied, we simulate the state changes directly in these physical representations, and then we render the prediction. And the generative model kicks in here again to refine the result, to ground its learned knowledge into the physical representation. And by keeping this loop running, the physical representation allows us to interact with it and allows us to have guaranteed consistency, while the generative model continuously grounds its knowledge into this explicit form that is simulatable and controllable. And we call this a physics-grounded world model. Now, let me show you how this key insight plays out in practice. I'll walk you through two core capabilities of world models. That is, recreating 3D worlds and simulating physical interactions within these worlds. I'll also show how physics-grounded world models can be applied to broader domains, such as engineering and scientific analysis. Let's start with world generation for now. So here's a demo from my work called Wonder World. We start with just a single image as shown in the left-hand side as input. And from this, we can generate 3D worlds that you can freely explore. Now we can move around and change viewpoints in real time, as you can see in this first-person view in the middle. And as we move to new areas, new things are generated on the fly. So on the right, we have this bird-eye view so that you can see how the world is growing as we explore it. Now, this task of 3D world generation is pretty challenging because we don't have a large data set of diverse 3D worlds. So prior work has focused on two different approaches. Now, the first approach is pure generation, where the technical idea is to train an end-to-end neural network that takes the previous frame as input and predict the next frame. This allows you to create interesting new contents, but it lacks the guarantee of consistency. So you can see that the textures, like the grass and water and the snow, are actually flickering pretty heavily as the camera moves. And the second approach is pure 3D generation, where you just reconstruct whatever that is visible in the input image. Right? This guarantees the consistency because everything is anchored in 3D geometry, but it cannot create anything new. So that's why in the black regions, there's simply nothing to show because you are restricted to the content that is present in the input image. So a natural idea is to combine both approaches. For example, we can reconstruct whatever we see in the input image, and then when the camera moves to a new location, we just in-paint the missing regions. But this approach doesn't provide the geometric grounding, and thus you see the inconsistency here. So every time you move your camera to a new location, there's something new pop up, and that breaks the consistency. Because now the new contents is only in-painting to the screen rather than grounded in 3D geometry. So the missing piece here is geometric grounding, and this is exactly where our framework comes in. For this problem, the physical representation is 3D geometry, and the generative component is image outpainting. Now, the key here is how we integrate them by grounding. So we render the 3D geometry, we outpaint the missing regions, and we reconstruct it back to 3D representation. So then every piece of the new contents is grounded in geometry before we move on. Now, let me show you how this works concretely. So we start from a single image. We estimate steps and reconstruct the 3D point cloud for the initial scene. And now we move the camera to a new location and render what we can see from the existing 3D content, which give us a partial image. We then use the image generation model to outpaint the missing regions, which produces a complete view. And next, we estimate depths for this new view and reconstruct the 3D scene and ground it with the 3D world we already have. So we repeat this again and again, and that gives us a complete world. Now, this is what we get, a large and coherent 3D world that you can freely move around in. The 3D reconstruction gives us the controllability around the viewpoints and the guaranteed consistency, while the generative model lets us to effortlessly create diverse and realistic contents. I introduced this approach in Wonder Journey in late 2023, and here are some results. Now, each of this is a 3D world generated from a single input image, where you can freely navigate through all of them. And you can see the approach works across a wide range of visual styles and scene types. For example, you can go from a real photo of an outdoor scene or a painting of an indoor scene. And you can notice how as the camera moves, how the geometry actually remains consistent even when you are continuously generating new scenes. And that's the benefit of grounding generation in 3D. And although Wonder Journey can generate large and diverse 3D worlds, one caveat is that it actually takes 10 minutes to create a single scene. And to create a large world, it easily takes hours. But if we really want to explore these things interactively, then we need the generation to be much faster. And the technical challenge here is that the 3D generation itself is pretty slow. So to address this, we introduce a new scene representation called the fast layer Gaussian surface. Here, surface represents a surface element, which is old computer graphics concept. So we borrow from that. And each surface is parameterized by its RGB color, its XYZ position in space, its 3D orientation in space, its radius, and its opacity. Now, reconstructing a large collection of these high-dimensional circles is pretty slow. So the key idea is that we can drastically reduce the dimension of our optimization problems by leveraging pixel-level geometry. So we estimate pixel-aligned depth map with a foundation model, and then we invert a camera projection model so that we can unproject each pixel. And this provides a geometry-based initialization for RGB and XYZ. And similarly, we can use foundation model to estimate surface normals and use that to estimate the orientation of all the circles. And then with the XYZ position and the spatial orientations, we can estimate for its radius by solving a Nyquist sampling equation combined with the camera projection model. And here the intuition is that, well, a circle has to be bigger if it is more distant from you in order for you to observe it. And if it is more slanted, then it also has to be bigger for you to observe it. And now, the only thing left was the 1D opacity. So here we reduce the dimension of the optimization problem to accelerate it by more than 100 times. So here is a illustration of the optimization reconstruction process. And here I actually have to slow down the playback speed of the video by 10 times in order to see what is happening here. Now, this fast Gaussian circle representation enables interactive user control over both the content and the camera control. So this was not possible with prior approaches because pure generation model doesn't have the physical representation for geometric grounding and for consistent real-time rendering. And pure reconstruction cannot create any new content. But our approach can give you both. And here's one more example showing a pre-generated 3D world. From a single image on the left-hand side, we create a full 3D world that you can freely explore, and the user can extend it by generating new content in unexplored regions. Now, this line of work has strong impact in both industry and academia. Now, in Professor Feifei Li's well-known talk on spatial intelligence, she used my Wonder Journey results to illustrate the vision of generating explorable 3D world from only images or text. And this vision has become the foundation for her startup called the World Lab in late 2024, which also draw inspiration for my series of work. Now, World Lab has already built products serving real users, and it is very interesting to see research ideas turn into multi-billion-dollar startup. And besides the industrial inspiration, my work also leads to a booming of world models. So after we introduced Wonder Journey in late 2023 and Wonder World in early 2024, this direction has really taken off. Now, here is just a snapshot of the follow-up research coming in the past 2 years. This work comes from both academia and industry labs. And you can see the pace is actually accelerating with new works appearing basically every month. And interestingly, many of them adopted the Wonder or World naming convention in their titles. And given this boom of world models, I'm continuing to push this direction even further. But rather than improving them, I focus on identifying the next open problems. So there are so many work on world models, and there will certainly be even more. And the pressing question now becomes, how do we actually measure the progress? We propose World Score, which is the first evaluation benchmark for world generation. And World Score addresses the key challenge in evaluating world generation. That is, while it is straightforward to evaluate the semantic content in the generated world, such as, is this object there? It is still very difficult to evaluate the spatial content, such as the spatial layout or the 3D consistency. And our key idea is to introduce spatial prompt. Technically, it is camera trajectory, so that we can specify spatial content in the world generation task. We also curate a large data set, and we maintain a leaderboard so that World Score can serve as a practical tool that everyone working on world models can use it. And besides the evaluation problem, recently I identified a new open challenge in my work, Wonder Zoom, that is multi-scale world generation. Although all existing work on world generation focuses on single-scale 3D scenes, the world is intrinsically multi-scale. For example, you can zoom in from a city-level overview all the way down to the fine-grained details of the feathers of a bird or to the details on the car. And both World Score and Wonder Zoom presents new problem definition. And I believe there are many more such exciting open challenges waiting to be explored. For example, how do we generate dynamic and self-evolving worlds? How do we generate fully editable compositional world with disentangled geometry, material, and lighting? So these are what makes this very, very exciting. So that's the first pillar, 3D world generation. But generating a static 3D world is only half the story. The other fundamental capability of a world model is to simulate what happens when we act in that world. So let's talk about simulating physical interactions. And remember the question that I started with? What would happen if I could actually interact with the Wonderland? Well, now, please. Sure.
How is consistency achieved?
Yeah, so
It's not very clear.
yeah, so here the consistency specifically refers to the geometric consistency. That is, for example, if you move your head around and you move your head back, is the content still there? Or if you view some content in different perspectives, is that 3D consistent? And here, in contrast to generative model, which generates a bunch of frames without geometric grounding, what we do is that we actually render, which is a deterministic process, from the geometric 3D representation of the scene. So since this is a deterministic process with the 3D content fixed, so we can guarantee the consistency every single time we went to the same location.
I guess something like traditional reconstruction, if you just multi-view stereo, you get a lot of drift as you go, so it's very hard to do, say, loop closing and get that to be consistent. And it seems like at every step you commit to the current contents of the 3D scene. So does that cause problems to the reconstruction?
Let me understand the question. So you're saying that for multi-view reconstruction, we also have a standard, have a 3D representation there. And then
So like one traditional problem is it's hard to construct as you go and maintain consistency because of errors.
Yeah, exactly. So we actually skip one of the technical part. That is, we actually, when we estimate the depths for the reconstruction, we actually have a conditioning estimation, which estimates the geometry conditioned on the existing geometry, so that we make sure that, for example, there's no seam between the two parts of the geometry that we just built versus what is existing there. So yeah, we do have the design to make sure that kind of consistency. Yeah, thank you. Okay, so yeah, let's move on to the simulation of physical interactions. So now we can answer the question of what happens if we could really interact with the Wonderland, right? So here's the Manhattan's Tea Party. You can imagine, if we pull the honey stick back and forth, then we probably want to see that the honey drips down under gravity, and it also moves slowly over the cake because it is pretty viscous. And we can also imagine if there is a gust of wind blowing from the left to the right, then Manhattan's hat will probably fly off, and his hair will be swaying in the wind. And we can also imagine if we really knock the wine glass over, then it will fall down, and the wine will spill out. Now, let me describe this problem more precisely. So physical action can take different forms according to the application domain. But here we consider a basic and general form. That is 3D forces, such as pull or push something, or 3D force field, such as gravity and the wind. For example, given this input image on the left-hand side, now if we apply gravity field to this scene, we probably want to see that the yellow duck drops onto the water and gets supported by the buoyancy provided by the water, and the water also gets splashes and ripples in response to the hit. Again, we see the same branches of two prior work trying to approach this problem. Now, pure generative models like Sora 2 produce visually interesting videos, but they have no interface for physical actions. So you cannot tell Sora to apply gravity to this specific scene and predict what happens. And pure physical modeling approaches reconstruct 3D geometry, estimate material properties, and then run the physics simulator to predict what happens. Well, but this approaches requires the complete and accurate physical state to function correctly, which are generally not available from a single image. And just like before, a naive combination doesn't work either. So if we simply run a physics simulator and then apply a video-to-video translation model, then the result still lacks physical coherence because the two components only communicate through pixels. But the physical states that actually drives the underlying dynamics are lost. So the question is, how do we integrate them properly? And here's how our framework instantiates for this problem. Now, the physical representation is approximate 3D physical states, which are not perfect. And given a physical action like a 3D force, we run the cross approximate simulator to predict the next physical states. And the generative component is a video generation model here, and the key is how they communicate. Now here, the simulator renders the prediction into pixels, and the video generator refines them. And the refinement is grounded back in 3D physical states. Now, let me walk you through how this works. So we introduced a technique called hybrid generative simulator in my work, WonderPlay. Now, starting from a single image, we first reconstruct the 3D scene using WonderWorld, and then we estimate material by a vision language model. And then we pass everything to our system. Now, the physics simulator takes the 3D state as input and then runs a coarse simulation with the action. And the action here is gravity on the smoke. So we see that the smoke rises up and heat the shows. Now, as you can see, the result doesn't look realistic because the smoke is too sticky and the motion is too stiff. And that's because we are working with approximate states, so that's expected. And next, we pass the physical states to condition a video generator. The video generator refines the motion and the appearance, producing a much more realistic video. And finally, we use this refined video to update the 3D physical states, which now give us a refined simulation. Because the result lives in 3D, you can render it from novel viewpoints freely. And here, the core technical challenge is that how do we actually communicate the physical states to a video model? Now, video model lives purely in the pixel space. So they don't understand 3D physical properties or 3D physical states. So somehow we need to translate the physical properties and states into a language that video models can consume and can understand. And our key idea is what we call bimodal control, where we render physical states into pixel-level signals that video model can consume. Now here's how. Our video generator is a diffusion model. So given a noise, a diffusion model transforms it into a video by gradually removing the noise. And here, the noise here is a learned neural network, and epsilon is a random Gaussian noise. But as we can see here, if we have no control at all, the generated video has nothing to do with our simulation. So we need to modify the diffusion process to control it with the simulation signals. And the first signal here is the simulated motion. So we render the 3D velocity into 2D screen so that there are optical flows. And we use the optical flow to modulate the noise inputs to the diffusion model. And this creates a structured noise. And you probably see that the pattern in the structured noise reflects the motion that is simulated. And the second signal is the simulated appearance. So we render the coarse simulation into a RGB preview video. And we blend this video with the modulated noise. Now, using this structured noise, we can substitute the render noise to pass in these two signals to video models. Right? And with this two channel of information, the video model is informed of the prediction from the simulator and refine it. Now, finally, there's an interesting point. That is, we can actually further control how much and where we trust simulation versus we trust the generation. So here we introduce a spatially varying control so that you can use a spatial mask to further inject the simulation information at any later time step. In short, you can control how much you trust the simulation by adjusting the diffusion step where you inject the simulation information. And you can adjust where exactly you trust it by the spatial mask. Now, finally, we use a photometric loss to ground the generated video back to our 3D states. And this closes the loop. So the result is a dynamic 3D simulation that you can render from any viewpoints. And our approach can handle a wide range of different materials and interactions. For example, here we apply a 3D force to pull this bolt on the top left. We pull this bolt to the right-hand side. Now, this bolt can be seen as a rigid body interacting with the liquid underlying it. And we can also simulate the wind on this T-shirt, which is a kind of cloth, or simulate wind on this deformable object on this tree. And we can also simulate gas interacting with rigid object, as shown in the show example, and rigid objects colliding with each other in the second last example. And we can also deal with granular materials like sand and snow. Now, this line of work also categorized a growing direction that I call the generative simulation, where the technical idea is to integrate physics simulation with video generation models to simulate physical interactions. And after the release of my earlier work called PhysDreamer in early 2024, this, which is the first work in generative simulation, this direction has rapidly taken off. So you can see this phys naming convention in these papers, just like wonder or world in the world generation papers. So why does generative simulation matter? Well, here's one example. Given a single image of a new scene, we can simulate what happens if a robot is manipulating objects in real time. Now, this was not possible before because pure video models cannot accept arbitrary physical action as input. And the pure physics simulator requires perfectly reconstructed or synthesized 3D scene to correctly function. So this is the first step towards a vision of physical AI, where we can transform any image or video into an interactive environment for training physical agents. And notably, industry has also been converging on the same problem. For example, NVIDIA's recent research efforts suggest that action-conditioned world models are becoming a central problem in physical AI. So we have now seen the two core capabilities of world models, that is recreating 3D world. Steve.
It's like, so can you do like real 3D physics, or is this just kind of like 2D or 2.5D physics?
Oh, yeah, everything here actually happens in 3D. So for example, in WonderPlay here, what we are doing is that we actually reconstruct the 3D geometry and estimate material for them, and then use an off-the-shelf simulator that lives entirely in the 3D space.
But you really only have like the surface, the front-facing surface. You don't have like a full, volumetric 3D.
Oh, actually, we do have. So for the background, we actually only model the visible surfaces. But for the objects that we are interacting with, we actually reconstruct the full geometry of it, rather than only the forward-facing surface. So yeah, here we actually, there's some technical details. Like we actually introduce a new representation called topological Gaussian surface, where we build upon the Wonder World representation, but add one more topological connection to all the different elements to represent the object's full geometry, so that we can simulate on them.
Then but it seems like the way that you're adding that physics constraint is in a 2D flow field, right? Or is there like a 3D, flow that somehow you're using?
Yeah, so the physics constraint here actually is reflected in the simulator itself. Because when we simulate it, essentially we're discretizing the governing equation, PDE, of that particular type of material. So the physical priors, in some sense, is injected in this step. But later on, we will see so in the third part of my talk, I will also talk about another way of injecting physical prior, that is through a soft constraint by converting governing equations into a loss. So yeah, thank you, Steve. So we have now seen the two core capabilities of world models, but the utility of physics-grounded world model actually go beyond AI itself. It can go further beyond. So for example, they can be applied to domains in engineering and scientific analysis to solve hard problems in their domain. For example, it can be applied to reconstruct different types of materials from videos. Now, let me walk you through fluid analysis to showcase this capability. So fluid analysis is critical in many engineering applications. For example, in thermal engineering, immersion cooling is an important technique. And engineers need to measure the fluid flow and to simulate any design changes so that they can maximize their thermal performance. And traditionally, measure fluid fields is relying on techniques like particle imaging velocimetry, or PIV, which requires specialized equipment in a lab control setting. Now, it works well in a lab, but it actually has limited applicability in real-world scenes. On the other hand, video is everywhere. It is cheap and easy to capture. So a natural question is, can we actually reconstruct and analyze fluid dynamics directly from videos? Now, this is exactly where physics-grounded world models come in. So let me describe this problem more precisely. So given a single video of fluids on the left-hand side, we want to recreate the 3D fluid and its 3D velocity field as shown in the middle video. So here, I'm rotating the camera a little bit when we render it, and we use the arrow to showcase, to visualize the velocity. And we also want to simulate possible physical actions, such as adding the wind. Now, you can notice that the goal is actually aligned with world models. That is, we also want to recreate the physical system and to simulate the possible actions in it. So we can frame it as building a specialized physics-grounded world model for fluids. But analyzing fluid from a single video is a very challenging problem. So prior work has approached this problem by physical modeling to reconstruct the 3D fluid field. But all of them require multi-view videos as input, and they all fail with a single video input. Because monocular reconstruction of fluids is simply too unconstrained. For example, fluid has strong self-occlusion, has depth ambiguity, and the 3D fluid motion is simply too complex. And besides the challenge of monocular fluid reconstruction, there are two more technical challenges, including how to recover underlying velocity field from only the visual observations, and how to do prediction with noisy reconstruction. Now, we can actually address the third challenge by using our hybrid generative simulator that we just talked about. So I will focus more on the first two challenges here. Now, to address these challenges, we built a specialized physics-grounded world model called Fluid Nexus. The key insight to address the first challenge is that we can leverage both the visual prior from generative learning and the governing equation from the physical modeling so that they can serve as complementary constraints to regularize this ill-posed problem. Concretely, we train a novel view video generator to synthesize multiple novel view videos that are synchronized with the input video. So this provides constraint over how the reconstructed fluid should look like from different viewpoints. And we introduce a visual physical particle representation where we can enforce the Navier-Stokes equation to constrain the reconstructed fluid motion. And for recovering the physical velocity from only visual observations, the key idea is that the differentiable particle representation can actually bridge the visual representation to the underlying physical fields by analysis by synthesis. Now here's how. So specifically, our representation consists of velocity particles and radiance particles, where each velocity particle represents a small velocity field, and collectively, they represent a continuous velocity field in 3D space. And each radiance particle represents a small radiance field, where they are transported by the velocity field in a differentiable way. Now here, the radiance particle also allows differentiable rendering, which enables gradient-based optimization. So we can then use an appearance loss through differentiable rendering and differentiable transport to reconstruct both the radiance field and the velocity field. And in addition to the appearance loss, we also have physics loss derived from the Navier-Stokes equations. So the loss enforces that the reconstructed velocity field should be incompressible, and it should conserve mass and momentum during the transport process. Now, with both the physics constraint and generative priors, we can reconstruct the fluid fields from only a single view. And yeah, Ramjay.
Could you say a bit more about that previous slide? So your generative model is still working on pixel space, right?
Yeah.
And so you have this representation somewhere in the middle that you're extracting from pixel space?
Yeah.
How are you doing that part?
So yeah, actually the generative model lives in pixel space, and the underlying physical representation here, the visual physical particles, lives in a separate 3D space. So the way we connect them is through differentiable rendering and the differentiable transport. So basically, the goal here is to reconstruct both the underlying velocity field, represented by the yellow particles here, as well as the visual appearance, represented by the blue particles here. And the way we do it is that we first have initial guess for both the representation, and then we use gradient-based optimization by doing iteratively the transport and the rendering process, so that through this temporal sequence, we have generate a video from different viewpoints, and then we compare that video to the generated video by our multi-view video models. And that is one end. From the other end, we also have a physics constraint for the underlying velocity field, because Navier-Stokes equation describes the general property of the fluid velocity fields. So we can constrain the velocity distribution so that they are divergence-free and they do not lose the momentum and the mass during the transport process. So that's how our apply these two losses to them. In summary, the appearance loss bridges the underlying 3D representation to the generated pixels, that is videos, and the physical loss is directly applied to the physical space to constrain the reconstructed physical quantity we have.
So following up to that iterative optimization process is, even though one iteration of it might be differentiable, the entire process itself iteratively is probably not, right?
Yeah.
And so then how do you apply this physics loss through this 3D representation into your generative model?
Yeah, very good point. So what we're actually doing is so if we do the whole transport process, then yes, and the gradient will be super noisy. So what we do is incremental reconstruction. So we start with the first frame. So the video are already generated, and during the reconstruction process, we start with the first frame. And then once the first frame is reconstructed, we go to the next frame. And in this process, we can apply the physics constraint in the transition process. So yes, for the visual losses, we apply them in a frame-wise manner. But for the physics process, we apply for every single transition state in the discrete manner. Think around, Jake. This is another question?
Yes. So in your previous topic, you also talked about use the video to refine the physics model. So are they following the same method?
So you're talking about the connection between fluid nexus to like wonder play.
Yes.
They're similar in the sense that we all want to optimizing the underlying 3D representation. So in wonder play, the variable to be optimized is the underlying 3D states, which includes the velocity and the position of all the particles in 3D space. And here in fluid nexus, we also optimize the physical states, but in a slightly different way. That is, here the physical state specifically refers to velocity rather than like momentum and other properties. And otherwise, they're basically sharing the same spirits underlying with only a little bit of the technical nuances difference. Yeah. Oh, please.
So you mentioned that one potential application is PIV, or basically analysis of fluids and smoke and things like that. Now, the representation of the approach allows you to generate a plausible physical model. It doesn't necessarily give you the actual physical model, right?
Yeah, that's a very good point. So we actually have one experimental validation later on. In a few slides later, I will talk about a real application to thermal engineering fluids. So in that case, we will validate the velocity that we reconstructed. Yep. Fluid Nexus can recreate and simulate the fluid in the input video. And to evaluate the reconstruction, we record multi-view videos of the fluid scene. And here are some novel view synthesis results. Now, given a single input video on the left-hand side, previous state-of-the-art methods cannot reconstruct the scene at all. But Fluid Nexus can reconstruct and render reasonable novel view videos. And once we have the reconstruction, we can also simulate different physical actions. So here we show two examples. One is adding a wind, and the other one is adding an obstacle, so that we can create some object-fluid interactions. Now, this line of work also has real-world impact in broader domains, such as thermal engineering, as I mentioned. In that, boiling heat transfer is an important technique. And it is actually everywhere in our daily life. For example, it is in air conditioning in this building, and in refrigeration, and in thermal power generation. Now, analyzing boiling heat transfer requires measuring the 3D liquid vapor interfacial velocity, because that's the quantity that governs the heat and mass transfer. But this interfacial velocity cannot be directly measured by physical devices. So let me replay this video. Okay, so we extend Fluid Nexus to work with two-phase flow and to reconstruct these properties from only videos. Now here I'm showing a visualization of the estimated interfacial velocity of a boiling process. And one important point is to validate it. So we actually derive a bubble velocity, that is a global metric, from our recovered interfacial velocity. And we find that this derived quantity actually matches the physically measured bubble velocity very well. So you can see this curve aligns very well on the right-hand side figure. Now, this is very important because that creates the trustworthy over the results that we have. And this creates a new possibility in analyzing boiling heat transfer. For example, we may use this to verify the computational fluid dynamics results from these experimental measurements. And this work has led to an ongoing collaboration with thermal engineering people with a goal to build really useful practical tools for scientific analysis. So physics grounded world models can apply to address broad, there's one more problem.
Yeah, just a quick question. It's
Yeah,
great
sure.
to see the, that this lines up with measurements. But I'm curious how this compares in terms of computational complexity to like traditional CFD simulators and things like that.
Yeah, so traditional CFD is great in the sense that when you give the complete boundary conditions and the properties of fluids and all the physical initial conditions, then you can have very good and accurate results. But one problem with analysis based on CFD is that it is an open loop process. So you can build the best model that in your mind and use that to analyze your physical systems. But it is not really verified. So you get all this quantity estimation from CFD, and you believe that it is right. So there's a self-validation loop. But what we need, or what is missing here, is the experimental validation or experimental measurement of the quantity that estimated by CFD. So that's where the world models kicks in. That is, CFD goes from the physical state to the observations, and we go the inverse way, so that we can form a closed loop, ideally, to verify the CFD models. Please.
On the last slide, where you had the plot, you started off earlier on the slide saying that it's not possible to directly measure the velocity, and then you presented results in comparison to measurement. I don't know what you mean by measured here.
Yeah. So it is at least very, very difficult to measure the interfacial velocity. That is the velocity field on the vapor-liquid vapor interface, the 3D interface. That is very difficult to measure. But what we are doing in this comparison is that we first reconstruct the velocity on the interfacial, in the interface, and then use that to derive a single velocity of the bubble itself. And then the velocity of the bubble is measurable. So we are comparing this derived quantity to a physically measured quantity to verify that the interfacial dynamic itself is plausible.
Thank you.
Thank you. Okay, great. So physics grounded world model can be applied to address broader domain problems, including fluid analysis. Well, it is still preliminary, but it actually indicates the promising future of world models. So finally, I'd like to share some of my visions of physics grounded world models into the future. So first of all, I believe that physics grounded world models will be a fundamental infrastructure for various spatial computing applications in the future. But to achieve this vision, we still have quite some capabilities yet to be achieved. For example, if we want to deploy world models to metaverse, AR, VR, and the interactive applications, then we at least want it to be real-time, to be long-term consistent, and to have multi-modal output, such as audios and haptics feedback, and to be physically realistic, ideally. Right. I believe such world models could power the next generation of immersive interactive systems. And in my ongoing work, I am exploring extending current world model systems along each of these dimensions. For example, in Real Wonder, we try to boost the inference speed of the world model system from a very low FPS to an interactive rate. So here in the bottom left, we are showing a demo of Real Wonder where you can interact with it using 3D forces or force fields. And in another work called Perpetual Wonder, we explore how we can extend the simulation horizon so that we can predict the outcome of a long sequence of actions rather than prediction within a small time window. And one of the most promising applications of physics grounded world model is in robotics, where I envision that physics grounded world models will serve as a universal simulator to automatically create diverse and realistic environments to help robotics and embody AI. Now, a major bottleneck in robot learning is arguably the availability of diverse and realistic simulatable environments. And world model could provide the means to help address this by automatically generating these environments that robots could be trained or evaluated in. Now, I see this as a complementary infrastructure for robotics community by providing this automatically generated environments. And this vision is actually becoming reality as shown in this recent demo from World Labs, which aim to scale robotic simulation with generated worlds. And in my ongoing work, I'm taking first steps towards this direction in 2 ways. First, with a robotics collaborator from Northwestern and from Columbia, we integrate learned dynamics model, which can be seen as a mini world model, with predictive control, so that we can support planning for a real task, that is painting, as shown on the left-hand side. And in parallel, I'm also pushing world models towards simulating robot actions. Here in this example, we represent robot action as the end effector pose trajectory, and we simulate what happens if this is interacting with some particular objects. These are all preliminary results, but my goal is to develop this further into a useful tool to help robotics and embodied AI potentially. And finally, I'm excited to collaborate with people in science and engineering domains, such as thermal engineering, environmental science, and more. Here, I envision physics-grounded world models could potentially serve as an analytical tool to help address problems in their domain. Now, beyond computing applications, I believe world models have the potential to become a new kind of scientific instrument which can analyze physical phenomena that are difficult or expensive to study with traditional measurement techniques. And as a concrete example, my collaborators and I have been building a delicate experimental setup to collect real-world data on thermal fluid systems. Now, these high-speed images show the bubbles detaching and rising during a boiling process in these videos. And on the right-hand side, I show our multi-camera rig for flow boiling data capture. Now, building this setup from scratch means that we're not just developing algorithms, but we are designing the full pipeline from physical experiments to world models. So to summarize, we are now at a very exciting time to work on world models because they just started to work and they promise to transform many important fields as they further mature. Now, physics-grounded world models addresses the key challenges of obtaining both the physical action interactability and the degree realism by integrating generative learning with physical models. Now, I've shown this through the 2 core capabilities of world models, that is, generating 3D world and simulating physical interactions in the generated worlds. And going forward, I envision that physics-grounded world model will serve as a fundamental infrastructure for spatial computing applications, as a universal simulator to help robotics, and as an analytical tool for scientific and engineering problems. Finally, I want to thank all my wonderful collaborators and the supporters. Without them, this talk wouldn't be possible. And thank you everyone for being here and raising any questions. I think we still have 5 minutes to answer any questions. Please.
Has your fluid motion been used on like meteorological applications, such as tracking movement of clouds for larger objects? Like a lot of the examples used are like smaller objects, but could it be used, especially if you can measure like the wind speed in various locations and you have image of a cloud? Could you predict like weather predictions better?
Yeah, that is a very good point. So we are trying to do that. So that can be done from aerial images or satellite images. Although we just have some initial efforts on it, but I can say that I think it is promising. But in terms of how exactly that works, I think that remains as future research because we are just looking at, started to looking at the data yet. So yeah, I believe so, but yeah, it remains a future research, I guess.
Really fascinating work. I have a really specific problem. I mean, there are some physics problems that are really counterintuitive to humans in our middle school. For example, if you have a light air balloon inside a cart and you accelerate the cart, I think the balloon should move in a counterintuitive direction. So do the physics models get confused in these counterintuitive physical problems.
So you are mentioning a specific application. Let me try to understand that particular problem. So you have a balloon with a
Cart.
Of a cart.
And a balloon inside it. The end of the rope is tied to the cart, and I accelerate the cart. And the question is, how will the balloon move in comparing to the cart?
Yeah. So I think my physical intuition tells me that the balloon should be like going backward compared to the cart, right?
I don't know. I think, yeah. Basically,
So-
but it depends on whether it's a light air balloon or the air inside the balloon is heavier than the cart. So there's a middle school physics problem, which is really counterintuitive.
Yeah. So although I'm not too sure about that, but I think physics simulator can actually take into account for that. So we, in SIGGRAPH last year, I think I see some of the papers doing physics simulation for the, a kind of balloons, that can fold itself also from Stanford. So I would say that physics simulation is actually more powerful than we might thought in simulating this kind of physical phenomenon. And the physics grounded world model has this advantage that we can actually take the advances from the physical modeling side and integrate it into our system. So I believe so. Eventually, we will be able to address that. Yeah. Oh, yeah,
Actually, kind of building on that, can I understand your work as creating a good interface between existing physical models that people use to simulate and the generative modeling side of things, so that the best of both worlds can be achieved?
In short, I think that's a reasonable statement for that. But I think that's slightly different because it is not about only interfacing the two components, but also about the deep integration of them. Because technically, this is actually non-trivial. So as I shown in some of the examples before, if you apply a naive approach to combine both, then it doesn't really meet our requirement. For example, in the reconstruction problem, in the world generation problem, if you simply concatenate a reconstruction system with a imaging painting model, then you still break the consistency. So that requires careful design into the technical pipeline of how we actually couple them. And for simulation, similarly, if we for simulating physical interactions, similarly, if we apply a physics simulator and then we concatenate it with a pure video-to-video translation model, then we still have a result that breaks the physical coherence because the communication there is actually too trivial because we really want to have the underlying physical dynamics, the physical states, rather than just pixels communicating with each other. So I think in the high level, yes, but technical-wise, there are actually research questions to be answered.
Would it be like a physics-based, like case-by-case integration, or are there more like a universal idea?
Yeah, I think there's a universal idea, but for example, for particular representations and for particular physics solvers, then that has to be domain specific. But the way to integrate them into a single system, I think, is unified.
What do you do in case of visual ambiguity? Like if I pump balloon with air and then let it, tie it, let it go, pump balloon with helium, tie it, let it go, it will do different things, but from video or image, you cannot see what is going into the balloon. So there may be such cases, and especially the thermal case where how do you know from visual cue whether it's the temperature of some fluid?
Yeah, exactly. That's exactly why we need the physical modeling part. Because if you only have an end-to-end generative model, then it's super hard to specify this kind of physical conditions or boundary conditions for them. And that's where the structural interface provided by the physical modeling is important. So you can actually control the boundary condition, initial condition, physical properties, materials, etc. for the object that you are interacting with.
The user can provide that.
Yeah, exactly. Exactly.
Thank you.
Thank you so much.
Thank you everyone for coming and for raising